All right, let's dive right in. Today, we're exploring a truly revolutionary moment in the history of deep learning. We are unpacking the landmark paper, Going Deeper with Convolutions, which literally introduced the world to the incredible GoogleNet Inception architecture.
Now, to really understand why this paper is so legendary, we got to start with a fundamental paradox. Think about it. How do we make AI exponentially smarter, capable of understanding highly complex visual stuff, without just feeding it endless budget-breaking computing power? For the longest time, the go-to answer was just, well, build bigger models. But as you probably know, that brute force approach quickly hits a wall.
Which brings us to a pretty staggering number, 12. The GoogleNet architecture we're looking at in this explainer managed to achieve significantly better accuracy than the famous winning model from just 2 years prior. And get this, it did it using 12 times fewer parameters. It's just an absolute masterclass in network efficiency.
So how exactly did they pull this off? Well, here is our roadmap for today. First, we'll look at the deep learning dilemma. Then we'll see why we need to go deeper, followed by the Inception module explained. After that, we'll look at the magic of one-by-one convolutions, see GoogleNet versus the world, and finally wrap up with the future of AI architecture.
Okay, part 1, the deep learning dilemma and the scaling bottleneck.
To appreciate the solution, we first have to realize just how tough the problem is. Imagine trying to tell a Siberian husky apart from an Eskimo dog. Differentiating fine-grained visual categories like that requires massive network capacity. Plus, you need really expensive, expert human raters just to label all that training data. It's incredibly difficult, even for us humans.
The old-school instinct was to solve this by simply increasing the network size, making it wider and deeper by sheer brute force. But that comes with 3 massive headaches. First off, uniformly pumping up the size makes the network highly prone to overfitting, especially when your label data is limited. Second, anytime you uniformly increase the number of filters, you get a quadratic increase in computational resource use. And third, if those added weights just end up dropping to 0 during training, well, you've got a massive waste of computational capacity. You're basically burning through finite hardware resources for 0 gain. Not ideal, right?
Moving on to part 2, we need to go deeper, the Inception approach.
By the way, that title, it's a direct nod to the internet meme that actually gave this architecture its legendary codename, Inception. Now, the crucial paradigm shift here is that the traditional method relies on uniformly increased size. That just leads to dense, bloated networks, overfitting, and those quadratic compute costs we just talked about. But the Inception approach, it completely flips the script. Instead of just making everything bigger indiscriminately, it aims to approximate an optimal sparse local structure. But here is the absolute genius part. It covers that sparse structure using readily available dense components. It's all about being incredibly smart with your connections rather than just blindly adding more of them. And this elegant method didn't just appear out of thin air. The Google researchers were heavily inspired by theoretical work from Aurora et al., which actually echoes a famous neuroscience theory called the Hebbian principle. That principle simply states, neurons that fire together wire together. The basic idea here is that if you analyze the correlation statistics of a layer's activations, you can cluster the neurons that have highly correlated outputs. So you're literally building your optimal sparse structure layer by layer just by grouping what naturally fires together. Pretty cool, huh?
All right, part 3, the Inception module, processing at scale.
Let's look at how this actually builds mechanically. Imagine the naive version of the Inception module. Instead of forcing the network to choose whether it should look at, say, small details or large patches at a given layer, this module processes visual information at various scales simultaneously. It uses 1x1, 3x3, and 5x5 filters side by side, along with a max pooling path, and then it concatenates all those outputs into a single vector for the next stage. It perfectly aligns with the intuition that visual features should be abstracted from different scales at the exact same time. But there's a huge catch here. If you just stack these naive modules on top of each other, you hit a massive computational wall. Merging the pooling and convolutional outputs without any form of compression leads to an inevitable, disastrous computational blowup. Even just a modest number of 5x5 convolutions placed on top of a layer with a lot of filters gets prohibitively expensive. Within just a few stages, you'd create a mathematical traffic jam that would instantly shatter your computational budget.
Which brings us to part 4. The magic of one-by-one convolutions and dimension reduction.
So to see the clever engineering workaround that saved this whole architecture, we have to look at the insertion of one-by-one convolutions.
By placing these little 1x1 convolutions right before the heavy 3x3 and 5x5 processing layers, they basically act as dimension reduction modules. Think of them like a high-speed carpool lane. They compress the traffic, shielding the large number of input filters and shrinking their dimensions before the really expensive spatial convolutions even take place. And since they use rectified linear activations, they serve a brilliant dual purpose: compression and adding essential nonlinearity to the network.
And listen, this dimension reduction matters immensely in the real world. The authors explicitly stated their goal was to keep a computational budget of 1.5 billion multiply adds at inference time, ensuring this wasn't just some academic curiosity. By judiciously using those 1x1 dimension reductions, they kept this incredibly deep network totally practical. This meant the network could actually run on real-world mobile and embedded computing devices with low memory footprints.
Okay, Part 5. GoogleNet versus the world. The ILSVRC 2014 results.
The ultimate proving ground was the 2014 ImageNet challenge, and wow, the results were staggering. Back in 2012, Supervision won with a 16.4% error rate. Then in 2013, Clarify brought it down to 11.7%. But in 2014, GoogleNet, which was a specific 22-layer deep incarnation of this Inception architecture, absolutely shattered expectations with a 6.67% top 5 error rate. That is a massive 40% relative reduction from the previous year's best. And what's wild is they did it without using any external data to train their classifiers. Now you might be wondering, how on earth do you manage a network 22 layers deep, or 27 if you count the pooling layers, without running headfirst into the vanishing gradient problem? Well, to ensure gradients propagated back effectively through all those stages, they cleverly added auxiliary classifiers to the intermediate modules. Basically, these smaller side networks encourage discrimination in the lower stages, increased the back-propagated gradient signal, and provided some nice additional regularization during training. Then, at inference time, those auxiliary networks are just simply discarded. Oh, and the architecture didn't just shine in classification. GoogleNet completely dominated the 2014 detection challenge as well, hitting a 43.9% mean average precision. That literally almost doubled the previous year's accuracy. And what's even more impressive, they achieved this highly competitive result without even utilizing bounding box regression, which really just proves the raw foundational strength of the Inception design. Finally, Part 6, the future of AI architecture, moving beyond brute force. Looking at the lasting impact of this engineering marvel, the ultimate takeaway from this explainer is the absolute validation of their core thesis. Approximating optimal sparse structures with readily available dense building blocks isn't just some fascinating academic theory. It is a highly viable, deeply efficient method for scaling up neural networks. They proved once and for all that you don't just need more brute force computing power to get exponentially smarter AI, you actually need smarter, more refined network topologies. Which leaves us with a truly exciting prospect, one actually posed by the researchers themselves. If we can successfully approximate optimal sparse structures with dense components to completely revolutionize computer vision, where else can this algorithm revolutionize AI? I mean, if automated systems start building topologies based on these exact principles for entirely different domains outside of vision, the possibilities for efficiency and accuracy are pretty much limitless. Thanks for joining me on this deep dive into the Inception architecture. Keep questioning the structure of things and keep learning.